Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on parameters. Okay, so for this video, okay, I'm going to have an example. How can we actually convert the S parameters to Z parameters? Before I come into this example in this video, okay, I'm going to explain why we need to convert S parameters to Z parameters. So this will be the objective of this video. This will be the part 9 series discussion on parameters. So guys, if you're keen to know more about parameters, okay, such as Z, Y, S, A, B, C, D parameters, or even H parameters, okay, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on parameters. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, guys, you can always ask me your question through the comment. Okay, before I continue, okay, I'd like to urge you guys to help this channel by like this video. Okay, so maybe you can also suggest which part of this video which you like the most. Okay, so because the more you guys actually press the like button, this video will have a higher chances to reach out to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly understand, okay, why we need to convert S parameters into Z parameters. Okay, so when we actually convert from S parameters, okay, so S parameters is also known as scattering parameters to Z parameters. So this Z parameters is also known as impedance parameters. It's often necessary, okay, for several reasons, okay, particularly when we actually working with different model or framework in electronics and RF engineering. Okay, so here are some reasons, okay, why this conversion is needed. Okay, so there are actually 6 reasons. Okay, the first reason is because there are different representation of network. Okay, for S parameters and Z network, they actually represent different way to describe the behavior of an electrical network. Okay, as for S parameters, they are mainly used for high frequency application. Okay, as they describe how signals are reflect and transmit through a network. Okay, so if you have seen the discussion on the S parameters, you know that when we actually use S parameters, it's because we cannot have so-called 0 ohm or maybe infinite ohm. So therefore, or open or short circuit, which is mean. So therefore, we actually describe the circuit by the reflection and also the transmit signal. Okay, so basically they relate the input and output voltage and current to the incident and reflected wave. So basically, this is the purpose when we actually use S parameters. As for Z parameters, okay, so they are often used in low frequency. Okay, so S is for high frequency, Z for low frequency. Okay, such as we do a simple form of circuit analysis which don't involve high frequency, and also the design that involve impedance matching, as they relate the voltage and current at the port of the network in terms of impedance. So from here you can see that S actually relate the so-called circuit in terms of the incidence and also the reflected wave. As for Z, it mainly describes a circuit by using the impedance. Next, okay, the second reason is when we actually want to do impedance matching, then we consider to convert the S parameters into Z parameters. Okay, so the Z parameters directly give the impedance relationship between the port of the network when we actually design circuit that need to match impedance to minimize reflection or maximum power transfer. Okay, so when we actually want to do impedance matching, okay, we want to do a match, which means that the input must be the same. So hence, if we look at Z parameters, it will be much more easier as compared to looking at S parameters. So this is another reason, okay, why we need to convert S into Z is when we actually want to do impedance matching. Okay, so as is explained over here, so if you are working with an RF or microwave network and need to design circuit that match specific impedance, okay, convert the S parameters to Z parameters can make it easier to incorporate impedance values directly into the design. Okay, the third reason why is when we actually want to do the analysis, in a circuit design, okay, which means that much lower frequency as compared to the S. Okay, so when we actually want to do circuit analyze, okay, which means that it's most of the time low frequency. Okay, Z parameters are useful in circuit analyze method, okay, such as node or mesh analyze, okay, where the network impedance behavior is important. Okay, for example, in analog circuit design, Z parameters are used for describing network in terms of voltage and current relationship. Okay, S parameters, okay, while they are actually based on the incident and reflected wave analysis, hence they may not provide direct impedance information, making Z parameters more suitable for certain analytical method in circuit design. Okay, so this is the third reason. Come to the fourth reason. Okay, so it is always simpler. Okay, when we actually work at low frequency, it will be always simpler to work in a Z parameters. Okay, for low frequency circuit or design where the network behavior is dominated by resistive element, okay, like DC or low frequency, or maybe some AC circuit, okay, the Z parameters are more easier, okay, because they represent the network in terms of resistance, reactance, and also inductance. Okay, so basically they are much more easier, okay, to calculate as compared to the S parameters, okay, which are based on wave scattering and the transmission line theory. Okay, they become less useful when we actually do at low frequency. Okay, since wave propagation effect are less significant. Okay, so basically if you recall, okay, for S parameters, okay, we are going to have a lot of so-called wave propagation. Okay, at low frequency, we assume that this wave propagation is so-called minimum or don't even exist. Next, okay, when we actually do some computation, okay, we need to have some form of convenience. Okay, so in some case, okay, it might be computation more convenient to work with Z parameters. Okay, especially when using certain software or simulation environment. Okay, for example, Z parameters are often used in simulation for steady state analysis, where the system impedance matrix is important for solving voltage and current distribution. Okay, so come to the last, okay, when we actually want to do conversion back and forth, okay, between parameters, which means that from Z to Z or S to Z and then vice versa again. Okay, so sometime, okay, you might need to convert different parameters types because of different design phases or tools used. For instance, you may begin with S parameters from measurement or simulation, but need to use Z parameters for further analyze or design steps. Okay, in some practical cases, you may have a system or component that is categorized in one set of parameters, for example, S parameters. Okay, but the rest of the system is categorized in another form, okay, which is the Z parameters. And because of this, okay, we need to do some form of conversion so that we have a seamless integration. Okay, so basically, these are the 6 reasons why we want to convert S parameters into Z parameters. Okay, so what will be the conversion process? Okay, the process of converting from S parameters to Z parameters, okay, involve, okay, some mathematical relationship between the two. Okay, so basically this video, I will give you an example. How can we actually convert from S to Z parameters? Okay, S parameters actually relate to the incident and reflected wave. Okay, while Z, which I have already mentioned earlier on, is actually relate to voltage and current. Okay, so therefore we need to have some form of conversion formula which depend on the specific network port. Okay, so most of the time we actually take the characteristics impedance of the system to be equal to 50 ohm. Okay, so for the two-port network, the Z parameters can actually derive from S parameters using matrix operation involve the network characteristics impedance. Okay, so let's take a look. Okay, how can we actually do the conversion? Okay, so this is a table that I actually got it from Professor David Poza so-called textbook here. So now we actually want to do the conversion, okay, the from the X parameters to the Z parameters. So these are all the set of equations that I need to calculate. For example, for Z11 will be this equation, Z12 will be this equation, Z21 will be this equation, and last but not least, Z22 will be at this equation here. So basically over here, you can see that we can actually convert various form of parameters into another form of parameters. So basically this video, as I mentioned, will be convert the S parameters into Z parameters. Okay, let's take a look on an example to understand this. And before I come into this example, okay, if you have learned something from this video, again, urge you to help this channel by like this video. And those who are new, okay, please consider to subscribe and turn on your notification bell. Once again, thank you so much. Let's take a look on the example. Okay, so before we come into the example, these are the formula that I mentioned earlier on. Okay, so basically, I just want to make this delta to be equal to this. Okay, because if you look at the formula, okay, you can see that all these, they are actually similar. So I just want to make it easier so that the formula don't look so tedious. So basically, these are all the formulas that we actually require to convert S parameters into Z parameters. Okay, so let's start. Okay, so basically we have this set of S parameters and we need to convert them into Z parameters. Okay, so basically, as I mentioned earlier on, most of the time we take the characteristic impedance to be at 50 ohm. Okay, most of the times, most of the port, they are actually all at 50 ohm. So first thing, okay, so this is a formula. So first thing is we need to calculate this so-called delta. So remember this delta equation is here. So I have rewrite this equation here. So we have all the S parameters here. So this is 1 minus S11. So this part here is S11, as you can see from here. 1 minus S22. So 1 minus S22. So S22 is here. So I write it here. So minus this is S12. So S12 here. So this is S12. And this is S21, as you can see from here. So I should get all this answer here. So next, okay, I'm going to do this 1 minus 0.3. So I get 0.7 and 1 minus uh 0.2. Okay, so basically this will be still become a minus because this is a minus here. So this become a minus term here. So this is 1 minus 0.4, which is positive 0.6. And again, you can see that this is basically minus. So minus minus become positive 0.3. Okay, so I guess this is a very common mistake. Please remember the minus is in front of the bracket. So this whole thing become minus. And same for here, this is minus. So minus minus become positive here. So I can also multiply these two things together. So if you punch your calculator, okay, you should be able to get this 0.025. Okay, so I won't be able to go through all the mathematical explanation. Okay, I mainly want to focus how can we actually convert the S parameters into Z parameters. Okay, once we get this, we can simplify. Again, we punch the calculator on this part. We should be able to get this part here. Okay, and then we minus this 0.025, we should be able to get this term, which means that this delta, which is equal to this. Okay, so it's also important to write down what we have, what we found earlier on. So like 1 minus S11, which is 0.7 minus J 0.2, which I write down here. Okay, 1 minus S22, which is this part here, which I write down here. Okay, and then S12 multiplied by S21, which is 0.025, which I write down here. And last but not least, the word delta here, okay, which is 0.455 plus J 0.9, which I write down here. So this will be able to use later on. Okay, so once we have this, we are ready to do the calculation of Z11. Okay, so this is the formula to calculate Z11. Okay, so as I told you that since we have this 1 plus S11, which we don't have, okay, so this is 1 and this is S11 here. So 1 minus S22, which we already get, so 0.6 plus 0.3 here. So this part, S12 multiplied by S21, which we have compute earlier on. So from here, okay, we can easily obtain the formulas for this Z11, which is 89.45 plus J 38.35 ohm here. So basically from here, you can see that I actually use the S parameters to get the Z11 values here. So next, okay, the Z12, okay, so all these I will go a little bit faster. So this is the formula to compute the Z12. Okay, so basically again, you just need to put in all the values, you punch your calculator, you should be able to get this value. So basically this is for Z12, which is 19.06 minus J 14.76 ohm. Okay, so let's quickly move on to Z21. Okay, again, this is the formula. So again, I don't foresee any issue when you punch your calculator, you should be able to get this answer. Same for Z22 here. Okay, so basically, I think with this, okay, I think you are quite confident that you are actually able to convert the S parameters into Z parameters. So basically, I think this video, I have met the objective and I have shown you the formulas that are actually required to convert the S parameters to Z parameters. Okay, with this, I'd like to end my discussion. Please help to like and subscribe. Once again, thank you so much for your time. Thank you so much.